Next speaker is Saada from Paris. Please go.
Okay, so thank you very much to the organizers. I'm very happy to be here. Like Pablo, this is my first time in Portugal, so I really appreciate the city. I don't appreciate the rain at all, but okay, that's what it is. And so I will speak of very recent joint work with Thierry Gobron, who is now in Lille, about attractiveness and couplings for general exclusion processes. So I will first, after introduction, go to the model. Then what my questions are, is it possible to determine the set of extremely invariant and translation invariant for the system? And my wide line would be what happens for simple exclusion, because we'll see that that's what we aim at, and that's always more complicated. So I will then explain how things go for our general model. So let me first go back to simple exclusion. So Reda spoke of totally asymmetric case. So what's the point? You have particles on the line, or on some set Z or ZD or anything. And if you have a particle at X, it wants to jump to some site Y, which is chosen according to some probability transition P, Pxy, and it will jump only if the site Y is empty. So in fact, the conditions we have here on the configuration for the jump is that we need eta of X to be equal to 1, a particle on X, no particle on Y, and that's all that is asked for simple exclusion about the configuration eta. And the important property we'll look at is the attractiveness property, which has been looked at more and more a lot by Tom Liggett. And so what is it? So we have our particle system on a state space, which for us will be 0, 1 to some S, especially ZD. And we have a Markov process, a generator, a semigroup, and there is a partial order on the set of configurations, which is the coordinate-wise order. We say that eta is less than psi if for every x, eta x is less than psi x, and then a function is monotone if it's increasing with respect to this order, and we call M the set of monotone functions, and there is a stochastic order on probability. We say that nu is less than nu prime if nu of f is less than nu prime of f for a monotone function. And finally, we say that the process is attractive if initially we have eta 0 less than psi 0, then at any time t we'll have almost surely that eta t is less than psi t, which means that the semigroup conserves the monotone functions, or that the semigroup conserves the order, the stochastic order of measures. Okay, this is all classical. And still for simple exclusion. So the question is, we know, I'll show you again, that simple exclusion is attractive. And for simple exclusion, we know that the extremely invariant and translation invariant measures are the Bernoulli product measures. So can we extend those results to other conservative dynamics? So some time ago, already with Thierry Gobron and also with Lucy Faifrova, we looked at conservative particle systems of misanthrope type. Misanthrope type means that the jump rate depends also on the departure and arrival site, but there could be many more particles per site, not only one, it could be up to k particles. And the point is that we looked at multiple jumps, which means that you have simultaneously k particles jumping from x to y. So for these type of models, we looked at conditions to have attractiveness, then find the extremely invariant and invariant measures, and then also we looked at, is there a necessary and sufficient condition to have product invariant measures for this type of models? So this we did some time ago. And another type of exclusion model is the one I will speak of, general exclusion. And then we could also have the same type of questions for non-conservative dynamics. And this was also done some time ago by Davide Borello. Okay, so what's our model? Our model is you have jumps from x to y, as before, but then the rate is eta x1 minus eta y. Of course, you need exclusion, but then it's multiplied by some rate gamma eta of xy, which is independent of eta x and eta y since it's before, but it could depend on the whole configurations. It's something depending on the configuration. And And so, okay, we have this problem. So the first point is to find some existence assumption, which is here. Oh, sorry. So you have this existence assumption. And this is a conserved dynamics, of course, because there's a jump. And if gamma eta reduces to pxy, then we are back to simple exclusion. So for this type of model, we look for what happens. So let's go back to simple exclusion again. How does it work, attractiveness? It works through something called basic coupling. So if you look in the middle drawing, I don't know how to use that thing. If you look at the middle, you see that we will couple particles on. So up we have a configuration eta, below we have a configuration xi. And what is basic coupling? Basic coupling is the fact that you want particles to jump together from the same arrival site to the same from the same departure to the same arrival site, and you want the particle to jump together as much as possible. For instance, in the middle, you have two particles, they jump together. But on the left, you have just one particle, so it jumps. Okay, it jumps by itself. And you see also here something which is important, is the evolution of discrepancies for the system. So what is a discrepancy? A discrepancy is a site where you have one particle for eta and no particle for xi, or the opposite. And what you see on the left drawing is the fact that this discrepancy, when the particle will jump, it will move. The discrepancy moves from z to z minus 1. And on the right, so on the right it's different thing. Imagine you want that a particle jumps to the right. So what it will jump just by itself, because you need the same departure and same arrival self for basic coupling. So if it jumps by itself, what will happen? It will happen that you have a discrepancy, but then the particle goes, but there is a particle below. There is a particle at z for xi. So the discrepancies will merge, and you kill the discrepancies. Okay, for the moment, it's just I kill the discrepancies. But that's, as we see, this will be very important for the future. So this is so nice, basic coupling. Why don't we use it for the general systems? So that's just what I said you. Oh, so before going to general systems, just back for always for simple exclusion. So how do we get the extremal invariant and translation invariant? That they are the Bernoulli. So the proof goes back to Liggett, always. So if you have a particle mu belonging to this set, you take one of the new rows, you couple them through basic coupling, and the main part of the proof is to prove that you cannot have discrepancies of opposite sides, of opposite sign, like before. You see, like before, with this jump, with the last jump, you have the discrepancies which merge one with the other, and in the end, you have no more discrepancies of opposite signs. So that's exactly, this merging is exactly what happens with this proposition, which is the main thing. And then, okay, using some irreducibility, you prove that the two configurations are ordered, and so mu must be one of the new rows. So the main point is to prove that you cannot have discrepancies of opposite sign within the dynamics. Okay, so as I said, it would be nice to do the same thing for another exclusion, but what we can prove is that simple exclusion is the only exclusion process for which basic coupling is monotone. Meaning, if you take some general exclusion process, you do basic coupling, you assume it's monotone, then the conclusion is that all the gamma etas are equal and are equal to pxy, so in the end you get simple exclusion. So for general exclusion, you need to do something more, something different. So our strategy here was first to find some necessary conditions on the rates to have attractiveness, then to construct a coupling under which the evolution is, which is an increasing coupling, which means that it preserves the stochastic order between configurations. And if we can get such a coupling, it means that the attractiveness conditions were also sufficient. And then, okay, first we have, with this first coupling, we keep the stochastic order, but we want more. We want to look at discrepancies. So we modify the coupling in such a way that the discrepancies do not increase. But then we need more. We need the discrepancy to decrease. So we have to construct a third coupling under which discrepancies will decrease, and then we can end up and prove the extremal invariant and translation invariant. So I will show you after examples, and you'll see that in examples, if the example is simple enough, the first coupling will do everything. But if the model is more complicated, then you need a second coupling and even a third coupling. Okay, so as I said, the skeleton of proof for a general system is always the same one. Okay, it requires more technical steps, but it's always the same one. So if we assume some irreducibility, meaning that the point was on the previous slide where I showed you the discrepancies evolving for simple exclusion, they were close to one another. But if you have one here and one here of opposite sign, you need the first one to come and close to the second one. So for this, you need to have some paths. So you need the gamma eta to be able to build a path of open edges to go from one step to the other. So that's the first condition. You also need some more irreducibility on the coupling grades, which depend on the model. And like that, it's possible to prove, as for simple exclusions, that either you already have a one-parameter family of product invariant and translation invariant measures, then you prove that it's everything, like for simple exclusion, or you don't have such a family, but you can prove that this set is a family of translation invariant probability measures with parameter rho, which corresponds to the density per site. These mu rho are ordered, and this rho doesn't belong to everything. It belongs to some closed subset of 0, 1, which contains 0 and 1. And that's it. And this other part of the proof is similar to what I did some time ago with, in a series of papers with Christophe Bahadoran, Hervé Guillol, and Ravi Shankar. That's it. Is it okay for the moment? Okay. Okay, so here is our first result about the attractiveness conditions. So you see all those, you see big inequalities. So let me try to explain to you how it works. If I can manage with this. Okay, here it is. So what does it say? Let's look at the first condition. The second one is of the same type. So let's look at the first condition. So we take a general exclusion process, so with the rate gamma psi or gamma zeta. So if we take psi, two configurations so that psi is less than zeta, we will look at jumps. So first we look at jumps with some arrival site y. So if I take some y such that zeta of y is equal to 0, so my arrival site will be empty for zeta, but since I have this order here, psi less than zeta, it will also be empty for psi. So what is it on the left side here? Here you have possible jumps to arrive at y from site x, which is full for psi, but since we have this order, it's also full for zeta. And here you have a jump rate concerning only the first configuration psi. So what happens with this jump rate? It's some excess rate to jump from x to y. So we have gamma zeta, and we are assuming that there is more in gamma psi than in gamma zeta. So here there is a positive part. And so here we have a jump from x to y for psi. But the problem is that if a particle jumps from x to y just on psi, then on y, after the jump, you will have a particle on psi, but no particle on zeta. So you break the order. So the point is that you don't want this order to be broken. So you want to build a coupling such that you don't have this order broken. So you want the site y for psi to be filled by something. And that's what is done here. for zeta, sorry. So that's what is done here. On the right-hand side, you look at jumps for the second line. So zeta of x is equal to 1. There's no 1 on the first line. Psi of x is equal to 0. And there's a jump with a rate gamma zeta xy from x to y. So with this, if you use one of those jump rates, you'll have the particle at y, which will be filled for the configuration zeta, which is okay, since here it would have been empty, but then you fill it. So then you keep the order by building a coupling rate, taking into account that a jump of this type has to be balanced by a jump of that site. And since here you have less than equal, it means that it will be possible to find such a rate. And the second one is exactly the same type of inequality, but here instead of looking at arrival sites, you look at a departure site, and you see what happens if you have a jump from this departure site to all the possible y's. So you see here you have a jump to an empty, from x to an empty site y for zeta. And then if you do that, then you'll have, after the jump, someone on x for psi, but no one for zeta, so you need to balance it. And how would you do it? You would build with a jump from x to y for the configuration psi on a site which is empty for psi, but full for zeta. So this is, okay, these inequalities, we will guided to get them by a very old paper by Massey, which has nothing to do with probability, but with systems with denumerable state space. So we could prove these types of inequalities. So they are necessary. We can prove that. And then we need to prove that they are sufficient, building a coupling. But before going to a coupling, I wanted to show you how it works for some examples. Actually, I don't show you the examples we began with, which was an example of a lattice cast model, which was in the seminal paper by Spitzer, the 1970 paper, Interaction of Markov Processes. So he gave there some exclusion with speed change. And this model was studied by Liggett in the Saint-Flour lecture notes for 76, so the first volume he wrote on particle systems. And in that 76 lectures, what he gave was a sufficient condition to have attractiveness, and he built a coupling out of that. But with our conditions, we realized that his conditions were sufficient but not necessary, so we could refine them and, and build another coupling than his, but there are many possible couplings. Okay, so what I will speak about are two traffic models. So the first one is what we have called a range 2 traffic model. But for this model, we began with a totally asymmetric two-step exclusion, which was introduced by Hervé Guillol. So what is it? You have a particle at x, and it wants to jump to a neighbor to its right. So if site y is x plus 1 is empty, the particle goes. But it could be that x plus 1 is full, in which case it will go one step further and it will go to x plus 2 at the condition that eta x plus 1 is equal to 1. So that's totally asymmetric two-step. And you could do something similar by looking at totally asymmetric, what we call 2-star step, which means that to go to x plus 2, you need x plus 1 to be empty. That's another possible condition. And then you could mix both conditions and build this range 2 traffic model. So at x, either you jump to x plus 1, or you jump to x plus 2 with a rate alpha if x plus 1 is full, and with a rate beta if x plus 1 is empty. And this is just a combination of the two previous ones plus simple exclusion. And the proposition using our conditions is to say that this model will be attractive if and only if you have an absolute value beta minus alpha, which is less than 1, so equal to 1. So you see that okay, alpha equals beta equals 0, it's simple exclusion. Alpha equals 1, beta equals 0, you get totally asymmetric two-step. Beta equals 1 and alpha equals 0, the two-star step. Okay. Another model, which is another traffic model example that I knew by a paper of Gray and Griffith about a cellular automaton for traffic. And Gunther made me notice that, in fact, this is the famous KLS model, which I didn't know, sorry, Katz, Lebowitz, and Spohn. And so what is it? You have 4 positive parameters, alpha, beta, gamma, delta. And then what is the rate for a jump from x to x plus 1? You have to look at what happens at x minus 1 and at x plus 2. So either you have someone at x minus 1 and nobody at x plus 2, and that's the rate alpha, or you have no one at x minus 1, someone at x plus 2, that's the rate beta. Both sides full, rate gamma, both sides empty, rate delta. Okay, so it was known that this model was not attractive, so that's not a surprise. If we apply our inequalities, it doesn't work. So it's not attractive unless all the rates are equal and it's just back to simple exclusion. But what we found out is that if you take a symmetrized version of it, which means that alpha, we also look at jump from x plus 1 to x, and alpha will be the rate to jump if x plus 2 is full and x minus 1 is empty, beta if x minus 1 is full and x plus 2 is empty, and we keep gamma if both are full and delta if both are empty. And then what we find is that that symmetrized version will be attractive if and only if the rate satisfies some inequalities here. And okay, and what we could notice, for instance, is that if we look at something which has been much studied recently and is still studied, which is the facilitated exclusion process, it has those rates with beta is equal to delta is equal to 0, and alpha is equal to gamma is equal to 1. It's not attractive, we know that, but even the symmetrized version is not attractive. So that's kind of strange. So, okay, I did put some references for facilitated exclusion, but there are many more, I imagine. So I just quoted Ayer, Lebowitz, and Speer, which just appeared, or Baek, Barakan, Corwin, and Sweden, or Blondel, Erignou, Simon, and Saada. Okay, and then what about the coupling that I promised you? So I will not show you the form of the coupling rate because it's too horrible. I just want you to see what it looks like. So what's important here is that you will have jumps not only you'll have jumps from x1 to y1, from x2 to y2, and everything could be different. So it's not always jumps from the same, like basic coupling, same departure, same arrival, with a rate g here. And then you have the uncoupled, jumps from x1 to y1 and from x2 to y2. And so of course this will be a coupling. You need this g to be non-negative, you need this to be non-negative, and also this. And this is just the remainder, if you look at all those cases, to get the uncoupled jumps. So it's just these formulas here, nothing special. And what can we say about these jumping rates without giving them to you? What we can say is first that if we have the jump rate for psi zeta with the same departure and arrival, xy, xy, then it will be like for basic coupling, it will be like for basic coupling, it will be the infimum of gamma psi and gamma zeta. And if, moreover, you assume that psi equal to zeta, then we just get the diagonal terms, which are the only non-zero coupling terms, and marginals remain equal. So that's normal. But if we look at uncoupled jump rates, then we'll have that the G are non-negative only if the configurations are ordered. So the G will be non-zero only if we have either psi less than zeta or psi larger than zeta. And in that case, there will be non-zero only if they have either the same departure site or the same arrival site. So it's not completely crazy. And the point is that there will be, okay, complicated formula, but taking into account what I explained to you about the attractiveness conditions. So we need to balance some bad jumps on one side by some other bad jumps on the other side. And under the attractiveness condition, this coupling will be an increasing coupling. So to finish, I just wanted to show you what it looks like for two-step exclusion, the one I showed you at the beginning. So you see here, just to remind you the model, you can either go one step to the right or you jump 2 steps. Okay, so what are the coupling possibilities? If we have psi less than zeta, there will be only one really coupled rate, which corresponds to the fact that for psi we jump from x to x plus 1, and for zeta, psi and zeta, yes, for zeta we jump from x to x plus 2. So that's the only possibility. And if psi is larger than zeta, you have the symmetric case. But then, what about if we look at the uncoupled jumps that we get from here? We get here, for the first the fact to jump from x to x plus 1, here are all the other possibilities. We could have only this jump with someone here, someone here, nobody here. We could have here someone, nobody, nobody, someone. But this is exactly what we had for simple exclusion. So then we have the discrepancies here which will merge. So this is what we look for. So notice here that if this particle jumps, we just have, here we have a discrepancy, here also, and then if the particle jumps, we'll have the discrepancy which will move from here, from x plus 1 to x. And here we have another possibility, which is someone, nobody, 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 and then also the discrepancy will jump from here to here. Okay, and for the second marginal, we have someone, someone, nobody. So up you could have nobody, someone, nobody, and then also the discrepancy will just move from one side to the other. Or you have 2 other possibilities which are nice for us, which is empty, full, 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 empty, and then if this particle jumps here, then you see that we'll have 2 discrepancies that will merge. So we're happy, and also here, someone, nobody, nobody, someone, someone, nobody, and then also have the discrepancy which merge. So in that case, and we have symmetrical, of course, I didn't look at what happens in that case, but it's all symmetric. And so you see that with this first coupling here, we get what we want. We get stochastic order preserved, and we have the discrepancies that can decrease. So this model is simple enough to have everything with the first coupling. And also what I didn't mention is that in the coupling here, you can see that we have the same departure site for 2-step. If we look at the 2-star step, we'll have in the coupling the same arrival site. And if we look at more complicated, for the traffic model, it will be more complicated, and we'll have the second the traffic model with alpha, beta, gamma, delta. We'll have also rates. We'll have different types of coupling, and the second coupling, then we'll have rates from x1 to x2, and x1 to y1, and x2 to y2, which are all different. So it depends, I mean, the complexity depends on the complexity of the dynamics. And in that case, of course, we'll get that the extremal invariant are the Bernoulli product, which was already obtained by Guillaume, so this is not a surprise, but this is just another way to arrive at the result for this model. And I think I'm done, yeah. That's it.
Other questions?
Could you please detail a bit more the traffic model you have shown?
This one?
Right here, yes. So you said it's asymmetric, right?
Yeah, because it goes from x to, yeah, it's asymmetric. It goes to the right. Then we do a symmetrized version by adding going to the left.
Yes. I'm sorry. So could you please explain a bit more the intuition behind the law at the beginning for the system number 5?
Which
For instance,
I mean, here you have a jump from x to x plus 1. So what I didn't put, which is in front, is the fact that eta x is equal to 1 and
yes.
eta x plus 1 is equal to 0.
Yes, yes, yes. Okay, sorry. Thank you.
Okay.
Are there other questions? Yeah, just two small questions. So first, like, if let's say if we have a model that doesn't admit uniform Bernoulli invariant measure, then we are sure it's not attractive, right? It's like
No, I'm not saying that.
Okay. So this is a very first.
This is a different. This is just a different case where if we have attractiveness, we can still prove that there is a one-parameter family of extremal invariant translation.
Okay.
But it's the different family. We don't know what it is. It's not product. It exists.
Okay. So it's not like any attractive system will admit uniform Bernoulli.
No.
Okay. Great. Okay. Second small question. So do you know, or do you have any insights, or do you know if it has been studied, like this similar concept for multi-component systems? Is it like, let's say if we have some system with 2 species or 3 species, or then has been defined the concept of attractivity and
not that I know.
Okay.
Not that I know. Nothing more than the basic thing. Not that I know. But maybe. Yeah.
So this is also kind of a generalization of the porosity model, because I can see from the facilitated exclusion that the porosity is also, you can recover it from by choosing alpha, beta, and gamma, and delta.
Mm-hmm.
So what you call congestion there would be...
These conditions here? Yeah.
I think what you call congestion would be a jump rate of rate 2. A jump of rate 2, because you look, it's exclusion between x and x plus 1, but you also look at occupation variable
before and after.
1. Yeah, so it should also be within this class. I think.
Yeah, facilitated exclusion is okay. One of the cases.
Okay.
Other questions? We can thank Len, who was the speaker of it.